All right. Hey, everybody. Welcome back. We got some fun things that we're going to talk about in this video. We are going to pick up where we left off, so talking about and recalling the test for divergence. And then we are going to discuss the converse for the test of divergence. So we'll discuss what the converse statement is, and then we'll try to explore whether or not the statement is even true. Turns out it's going to be false, right? So the converse for the test for divergence will actually be false. Now, to show this, we are going to identify a very important series called the Harmonic Series. So we'll identify what the Harmonic Series is, we'll talk a little bit about it, and then we will prove definitively that the Harmonic Series diverges. All right, so first of all, where did we leave off last time? Recall the test for divergence, which was a really quick and easy check to see if a series definitely diverged. And the test for divergence stated, I'll read this second bullet point here is the more important one, or I should say the more meaningful one for our conversation today. If the terms of a sequence do not converge to zero, then the corresponding series must diverge, right? And so for example, this meant that if we had a series of the form, let's say 1, minus 1, plus 1, minus 1, plus 1, dot, 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 right? Just alternating plus and minus 1. That series definitely diverges by the test for divergence, right? The individual terms never go to zero. Instead, they simply stay plus 1, minus 1, plus 1, minus 1, plus 1, and so on. At the same time, if a series is known to converge, then the terms of that series must converge to zero. So this was a great test, very quick and easy way to see if a series diverges. What I am interested in exploring today is the converse statement. In other words, if a series has individual terms that converge to zero, is it necessarily true that the series itself converges? Right? So the converse statement, as a reminder, a converse statement is a logical statement in which the two sort of clauses, their order is flipped. So the converse statement reads that, it would flip the statement where the series converges, and it would flip the statement of the terms of the series converging to zero. So the question that we want to ask is, if the terms of a series converge to zero, does the corresponding series definitely converge, right? In other words, is this converse statement actually true? All right, so it turns out this statement is false. And so to discuss this, let's clear some of that. Yeah, to discuss this, we want to introduce a very particular and important series called the Harmonic Series. So the Harmonic Series is going to be a series of the form or in which the terms are of the form 1 over n. We'll add up all of these terms as n goes from 1 to infinity. So that's 1 plus a half, plus a third, plus a fourth, and so on and so on. Notice each of these individual terms is getting smaller and smaller and smaller, and in fact they're going to zero, right? As n goes to infinity, 1 over n goes to zero. So when it comes to the harmonic series, the terms of this series are going to zero, but the series itself diverges. Now, we still have to show this, right? This isn't clear, especially, not yet, not clear at all. But once we show that the series diverges, we will then know that this converse statement is false. In other words, there are series, and the harmonic series is exhibit A here, there are series whose terms go to zero, but which diverge. Okay, so let's try to show the divergence of the harmonic series. And there's actually a very slick and clever way to do this. We're going to do the following. I'm going to break this up into smaller chunks. I'm going to break up this first piece by itself. I'm going to break up these two pieces here, or these next two terms as a chunk. I will break up, I'm sorry, I'm doing that incorrectly. Let's try that again. I want to break up the first piece by itself. I want to break up the second piece by itself. I want to break up the next two as a group of two. I want to break up the next 4 as a group of 4, and so on and so on. So the next 8 numbers from 1/9 up to 1/16, those would all be there as well. And so what do we get here? Or why am I breaking them up this way? Well, this first number, that's just the number 1. It's just the number 1. The second one, that's just the number 1/2. But then here, I'm going to do something kind of clever. I'm going to notice that this piece, right, the 1/3 plus 1/4, that is bigger than 1/4 plus 1/4. The idea there being that the number 1/3 is bigger than the number 1/4, right? And so because 1/3 is bigger than 1/4, a third plus a fourth is bigger than a fourth plus a fourth, and that is by itself just equal to 1/2. So these two terms together are bigger, added together, are bigger than 1/2. The next 4 terms together, a 5th plus a 6th plus a 7th plus an 8th, notice that is going to be bigger than an 8th plus an 8th plus an 8th plus an 8th, right? Because a 5th is bigger than an 8th, a 6th is bigger than an 8th, a 7th is bigger than an 8th, and an 8th is just equal to an 8th, right? And so those 4 terms together will also be bigger than 1/2. Now they're not on the screen, but you can imagine the next 8 terms all together, each of those terms will be bigger than or equal to 1/16. And so we'll add up a 16th plus a 16th plus a 16th 8 times, and we'll see that that part is going to be bigger than 1/2. And so what we're going to get is we can keep breaking up the harmonic series into these different pieces, each of which, when we add those together, we'll get something that's bigger than 1/2. And so the end result is that the harmonic series is bigger than 1 plus a half, that was this piece, plus a half, plus a half, plus a half, plus a half, and so on and so on. And so the harmonic series necessarily diverges. Awesome. Very cool. Very cool. All right, we'll see you next time.